today. Welcome back. It's Monday, 9 September. This is CSC241 Computer Architecture, aka Computer Hardware. And does everyone see my screen?
Yeah.
Yes, sir. Okay. What you're looking at is a view of my screen, the instructor view in D2L Brightspace. You're looking at this class. We have 28 students and 23 of you have completed. Now it doesn't say who, okay? Fun fact here, if I select this option and then open this up, there's a fresh option to email the people who have not completed, and it shows their names in the BCC option of that email. So when that email goes out, if there's 5 of you, you don't get to see which 5 of you by looking at the address line still haven't completed that activity, right? So why am I sharing this with you? I am about to post 1.5, the assessment for this module, your first attempt of the Module 1 assessment. And it's going to be due by 10 a.m. Wednesday morning. We'll also conduct our first item analysis of assessment items to see what the outcomes were. And we're going to walk through those and take a look at where most students struggled, right? And then we're going to talk about how to reconcile those errors so that you can retake a different version, a slightly different version of the same assessment for higher credit. Now, I will tell you that this is uncharted territory for me. And normally those options are readily available, but this is a brand new system and it's slightly different than Blackboard. The one thing I want to impress upon you is this right here. There are 10 students who have yet to complete and submit their binary hex conversions worksheet, and you're sitting ducks. Let me say that again. I'm saying this with all the love in my heart that I can muster. I want you to think of me as a kindly old uncle, maybe a kind of half crazy uncle in your family tree, you know, a little off on those family holidays, sitting off in the corner mumbling to himself. And that's me saying, "Oh, they're headed for the cliff. Oh, this is bad," right? Trust me when I tell you, you want to give this an honest effort before you go into the assessment. The assessment is timed. You'll have so many minutes to complete it. And yes, you can pull up your handy dandy calculator and you can still cheat, okay? You can still go to the programmer view of your standard Windows calculator, and there's probably a binary or programmer view on a Mac or in Linux. But I got to tell you, there are some things you won't be able to fake, like the bit shift calculations and some of the other content. And we're gonna work cleanup on aisle 6 this morning. We'll be touching on the finer points in the material, both in the study guide and the addendum. And this is the starting point, though. Except for the article summary, optimizing your technology, binary hex conversions, and installing in the test HDL, that stands for Hardware Definition Language Simulator. That simulator, by the way, did I mention that it's what they use to design chips in factories now? Did I mention that they design it first in software and then they use the HDL simulation environment to create the machine language that it takes to render the physical version of the chip on a silicon die? Did I mention that? Did I mention that just 5 years ago, this kind of software was kind of exclusive to computer engineers and that it would cost anywhere between $500 and $2,500? And it's free, courtesy of your textbook publishers. And yet there are 12 of 28 in this class Well, actually, I got to do the math. Let me flip that. 16 of 28 who have not installed it yet. And let me say again, if you haven't completed 1.1, 1.3, and 1.4, you're not going to do very well on your first attempt of the assessment. And even with reconciliation and error correction, well, your second and final whack at the assessment with the new version may or may not be better. Okay, we have a question from, let's see, who was that raised their hand? Levant.
Yeah, I had a question. I didn't submit 1.4 yet because I have Java downloaded because I had to do like my coding, so CSC 118 and CSC 117. But when I tried to run the simulator, it was saying that I didn't have Java. So I was having trouble with that. I was waiting for you to come in today to ask you about it.
Actually, we made mention of the fix in either on the leading edge or trailing edge as we were closing out in class one day. And if you had already cleared the screen, you might not have heard it. So I'm glad you brought that up, Barn. And thank you for asking that question. So the easy fix is to go to this screen and there's an extra link for where you get Java if you don't have Java. And you just click that link and you load the software from that link and it will load the runtime edition, right? It'll load the other Java option, and then that will solve the problem for your load. Okay. And
Okay.
it could be that the Java that's loaded on your system is configured with a slightly different path and that the simulator doesn't know how to access that. And there's usually other fixes that you can apply related to the system path environment variable, but we're not going to go into that right now. What we'd like to do is get started with our review. So without further ado, what I'd like to do is segue into this information. We mentioned with bit shift calculations that there were double cautions, that you couldn't slide to the right if there was a 1 in the ones column for a binary value. So if you had 0001 and you needed to have or quarter or 1/8 the value of a binary expression, what you would find is that the 1 can't be shifted off that column because there's no more binary columns to the right. Does everybody know what I'm talking about? Explicitly. If I attempt to shift this binary value, and I want you to notice how I'm highlighting it. If I'm given a binary value that's expressed like this, and I want to shift it to the left, I'm really doing this. And as I move to the left 2 places, let's say I'm going left 2 places, I'm doubling and quadrupling what this means, okay? So this is 1, and that's 2, 4, 8, 16, 32. 32 is lit and 1 is lit. This is the binary expression for the decimal value 33. Does everybody see how I got that?
Yeah.
Okay, so I'm in binary terms, when I have a 0, that number place is turned off, so I don't add them. Remember, computers are only thinking in on and off. They don't even think in hexadecimal terms. Hexadecimal number or base 10 is our translation that allows us to do binary in our head, and it actually helps computers adapt too. That's another story for another day. But if I shift 2 places to the left because I need to quadruple the amount. 4 times 32 is 128. Or actually, I've got 33. So I want to quadruple that. It's going to be 128 plus 4, be like 132, I think. Anyway, what I'm actually doing is moving this here. So I'm moving this value 2 places to the left. And I'm moving this place 2 places to the left. So I advocate when you're doing these problems that you do just as I have done. I have modeled the steps that you follow to resolve bit shift calculations. You're going to open up a Word document, you're going to make it big, and then underneath what you're going to do is shift. There's 4 zeros here. So I'm going to shift, there's 3 zeros. I put a space, there's another 0, and there's my 1. And that's followed by 2 zeros. I should be able to show that I have shifted this here 2 places and shifted this here 2 places. I'm taking this entire binary value and I have to preserve the zeros in between the ones. Does everybody understand what I'm saying? So the leftmost one and the rightmost one, you have to preserve all the zeros in between. And you could get a mixed bag, right? Like you could get something that's like this. 0010 space 1010, right? So you could get more than one set of ones. That means you're taking this entire set of binary values. And if I'm shifting to the right, in this case, I can because my 1 is not on the border. It's not on the edge. I want you to consider the rightmost column to be like a cliff. So now when I do this, if I'm shifting to the right, I'd go 0001. And then let's see, this goes to the right as well. So first value would be a 0, and then a 1, and then a 0, and then a 1. So I can basically highlight this and show that it's the same combination of ones and zeros. It's just shifted one to the right. Does everybody see and understand what I'm talking about here?
Yeah.
So I can have this value, but I can't cut it to a quarter. I can't half a half. I can't go further to the right. This boundary is like a cliff right here. This boundary is like a cliff. It's not a yellow caution like danger, Will Robinson. It is oh, I have a 1 and it's on the rightmost boundary and I can't shift more to the right. Okay. All right. So there was a second caution. Anyway, use a bit shift method to calculate. We've done that. Let's look at your appendix. I mean, your addendum. Your addendum has important information. It's kind of hidden or embedded in your addendum, and it's fair game for assessment questions. So here, logic gates. When you see the term logic gates, we're talking about a digital component that's physical. It is a hardware equivalent of the Boolean operators. Now, one difference between hardware and software, a Boolean operator is the software equivalent in a programming language. It's the software equivalent of that same basic logic, and, or, and not, and, or, and not, and, or, and not. Those are the basic Boolean operators, the basic logic gate components. They are the smallest. It's kind of like, has anyone ever heard proton, neutron, electron? Has anyone ever heard those? Proton, neutron, electron, what am I talking
Yes.
about? I'm talking about the components of what? An atom?
Atom.
Yes. Yes. Excellent. Yeah, we came to the same Same answer at the same time, an atom. And if you change the mix of protons, neutrons, and electrons, don't you get different types of atoms, different elements? Yeah? Everybody knows what I'm talking about now? Now, if we mix Boolean operators together, what we get is called a Boolean function. And in its simplest form, you can have a single operator as a Boolean function. You can have and then in parentheses, you can have the input value, right? So what am I saying? You can have a Boolean function. It's stated as a Boolean function. Okay. So you could have an operator that's just a plus sign. Okay, that's a Boolean operator. Or you could have this. And this tells you I have the or Boolean operator, but stated as a Boolean function, I have the input value of 1. Okay? Does everybody understand what I'm talking about? Okay, we'll just leave it there. We'll put a pin in that. Not hearing any questions. So this is, if you have more than one logic gate connected with pins or wires, we'll get into this more in the next module. What you have is a compound logic gate, which is the equivalent of multiple Boolean operators that are stitched together to create a Boolean function, okay? You'll have the physical version, a compound logic gate, which is connected with wires, what we call pins. Logic gate pins are actually physical wires. We want to talk about the not again. What is special about not? We said that not reverses the value of the input. So if it's not 0, what's the answer? What's not 0 in the Boolean world?
1.
1 is correct. If it's not 1, then what's the answer in the binary world?
0.
0. Just remember, this is the operator that executes first. There's an order of operations that you must maintain. Not always executes first, then and, then or. And that's because not is a kind of mathematical or logical wild card. And it always takes whatever is there, and when it's used, magically, it's the other value. This is the equivalent of multiplication. Remember that multiplication precedes addition in the order of operations. You learned in mathematics that multiplication and division are to be executed in an expression before addition and subtraction. Now, there is an exception to that, and I want to cue you into that. Let's say I have 6 plus 4 times 3 equals what? Do I do this first before I multiply? Or do I do this first before I add? What's the answer? It's not a trick question. Someone please.
4 times 3 first.
4 times 3 first because it's multiplication, and we perform the multiplication operation before we add. And that's counterintuitive because our brains work as a reflex from left to right. So we tend to go ahead and do this. We get the wrong answer. Now, Is there a mathematical adaptation I can use to change that, to force it to be different? Let me ask the question again. Is there a mathematical adaptation to this expression I can use that would force the order of operations to occur differently?
Parentheses.
Yes. Yes. Oh, I love that. Thank you so much. It's parentheses. So if you have an expression within parentheses, you have to perform that first. You do the internal parentheses operations before you work outside the parentheses. So if I have something like this, now I have to do it first, even though multiplication precedes addition, I have to complete and determine the value of this expression because it's within parentheses. So I can force a different order with the creative use of parentheses. That is something we'll come back to, but I didn't want you to be tricked, okay? And it's really important that you know in this assessment, it's not going to be easy. I'm going to try to trick you because this is basic and it's counterintuitive that we would think when we see this, I read this as 6 and 4 equals 10. And that's addition. And that's a verbal thing. And I have to break that habit. I have to say 6 or 4 if I'm talking about Boolean operations. This is or. So when I read it, logically speaking, I say 6 or 4 and 3. Okay. If I didn't have the parentheses, I would read this out loud to say 4 and 3 is ORed with 6. Does everybody see what I'm doing here? 4 and 3 is ORed with 6. Kind of a different world, subtle difference, but profoundly important difference. Okay? How are we doing? Remember, this is the symbol for and, this is the symbol for or. Of course, it's easy to remember this is addition. Just remember that or is addition, and verbally you're going to be saying or. Okay? Now, this is really important to know with and. If all inputs are true, then the output is 1 or yes. So if I take 1 and 0 and 1 and 1 and 1, my output is 0. And I'm doing these calculations in a serial or series of operations. Serial or series. Everybody understand what I'm saying?
Like one after the other.
One after the other. Taking the first two values and getting a result. If I and 1 with 0, what do I get? A 0. So if I take that 0 and 0 with 1, what do I get? Oh, a 0. So technically that next value here is a 0, and that's ANDed with 1. So 0 and 1 is 0. Carry the 0 forward, it's 0 and 1. That's what's happening here. That's what's happening on a Boolean level. For and, it's very picky. All the inputs have to be 1 or true or yes in order for the output to be 1. Now with or, if I put plus signs in here, any of them have a 1, the end result is a 1. Profoundly different outcomes. In our next module, we'll be talking about how you can perform a Boolean operation. You can apply a logic gate and you can do it in parallel instead of in series. What am I saying? you can take a value like this and a value like this, and you can AND them, and in that case, you're doing it in each column vertically, okay? So there are hardware conventions that can perform parallel bit level calculations, 4 bits, 8 bits, 16 bits, 32 bits, 64 bits. Has anyone ever heard of a 64-bit processor? 32-bit processor, 16-bit processor?
Yeah.
8-bit processor, 4-bit processor? The thing that I want to impress upon you is that it is possible in hardware and in software to calculate in parallel the results with and or not. So if this is an or, if I'm oring in parallel, if I or 1 with 0, what's the first result I get here? Well, let's start on the least significant column. Okay. What's the result I get here at the end? If I take 1 or 0 in Boolean logic terms,
1.
it's 1, because if any of the inputs are 1, then I get a 1, right? Does everybody see what happened there? I have a 1 or 1. What's the next value right here?
0.
Oh, it's a 1. Because I have at least 1. I have a 1 at the top and a 1 at the bottom, so the output has to be a 1. I have a 0 and I have a 1. Are at least one of those values a 1?
Yeah.
The answer is yes, so my answer is yes. And I have a 1 and I have a 0. I combine those two with an OR, and then I get a 1. So if we OR these two and perform a parallel calculation of those two 4-bit values, which would be called a nibble or a D word, or I don't want to get hung up on that right now. But anyway, everybody know what I'm talking about? Okay, let's take the same value and AND it. Okay, 1 0 1 1 and 0 1 1 0. I AND this value. What do I get? Both values have to be 1. All values have to be 1 in order for me to get a 1 when I AND things. So what's my answer here?
0.
0.
A 0 is correct, because this one's a 0. Both values have to be 1. Now let's take this next column. Is this a 1 and is that a 1? If I'm ANDing those, what do I get? A 1. I'm going to go faster because it's almost time for us to be through. What's my next result for the third column, or let's see, 1, 2, 4's column? What do I get here?
0.
I get a 0 is correct. And I get a 0 because, well, there's a 0 here. How about this column that's 8? I'm in the 8th column. What's my result? Are both values 1?
0.
They are not 1.
No, so it'll be 0.
It'd be 0. Yeah, you see what I did there? I tried to trick you. Or I need another cup of coffee. That might be the case. Okay, so this is the result for AND, right? And this is the result with OR. Holy buckets. In this case, I take 4 plus 2 plus 1, 7, right? And I add it Well, I don't know. Do I have that right? I get 1, 1, 1, 1. Because I'm ORing. Here I'm doing and. I get a totally different value. Any questions?
No questions.
All right. If you see a variable, if you see an input and it's labeled with a letter, so typically the pins or wires of logic gates or the inputs of a Boolean operator, a Boolean function, they are sometimes represented as a letter, which could have a 0 value or a 1 value. If this J for Juliet has an input value of 1, the not operator or the bar instantly flips it to a 0. That's something that I want you to understand. So if I tell you, okay, this is an input for a Boolean operator, this is an input for a logic gate, and the input value is 0. What am I actually working with here? You'd say, well, it's a not 0, so that wild card just flipped it to a 1. So everybody understand what I'm saying here? All right, that's all we had for our review today. I want to wish all of you the best of luck in your first attempt of the Module 1 assessment. For those of you who do not complete the Boolean worksheet before you attempt your first whack at the Module 1 assessment, you'll need more luck. Hope I've made my point abundantly clear. Any questions, comments, observations before we clear today? Thank you for joining us. We'll see you on Wednesday. You'll want to attend the class on Wednesday because it's the first chance you'll get to see how item analysis is worked in session, how we go over the errors for the class, and how you can reconcile. So please stay tuned.